Thursday. Okay. Okay, let's talk about one-way ANOVA. One-way ANOVA is the way that we compare multiple averages, multiple means. Okay, multiple means. Okay. Okay, objective, be able to determine when the ANOVA F test, so the F statistic, is appropriate. Use technology to perform a one-way ANOVA F test and interpret the test statistic and p-value in context. Okay, what is ANOVA used for? Okay, ANOVA is called analysis of variance. It's analysis of analysis, AN, I'll put this in capital, AN, analysis of ANO of variance. Okay, which is like standard deviation. It's analysis of standard deviations. Okay, and we do this when we deal with means. It's the analysis of variance. Variance is just the square of the standard deviation. Okay. Okay, so it's the generalization of the two-sample t-test. So whereas the chi-square goodness of fit test was a generalization for the for proportions, right? So where we had P1 equal to P2 equal to P3 dot 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 dot, right? And or none were equal, none are equal, or sorry, at least one was not equal. That's the same thing what we did for the goodness of fit test for the proportions. Well, that's analogous to what we're going to be doing for means. Okay, so means is mu1 equals mu2 equals mu3, however many that we need to test. Okay, we're no longer doing just two samples, we're doing multiple samples. Okay, it's a multiple sample t-test is what ANOVA is. ANOVA is a multiple sample t-test. Okay, ANOVA is a multiple sample t-test. We're saying, are all of these similar or is at least one different? Okay, so is there a difference in the means of multiple populations or categories? Okay, it is often used to analyze experiments with multiple treatments or levels of a factor. ANOVA stands for analysis of variance. Okay, is there more variation between samples or within samples? Okay, between the samples or within the samples. Okay, name of the test, the one-way ANOVA F test, that's the name of the test, or just ANOVA for short. Okay, define the parameters of interest. Okay, that's mu I. Mu I means mu1, mu2, mu3, all of the i's for I equals 1, 2, 3, 4, 5. What are the hypotheses? Hypotheses is that mu1 is equal to mu2 is equal to mu3 is equal to mu4, blah, 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 however many parameters that I have that I'm comparing. And the alternative is that at least one of them is different. Only one has to be different for me to reject the null and accept the alternative. Only one has to be different. Okay, if they're all the same, then we accept the null. Okay, and we're using significant level here of 0.05. The requirements, each sample is taken independently. Each sample is of quantitative data. So this is, you know, a question of quantity, you know, like weight or distance. Okay, it's a definition of quantity. Okay, how much? Okay, instead of how many. Okay, so quantity asks how much. Okay, how much quality, that's an A, by the way, quantity, let me rewrite that, doesn't look good. Quantity is how much? Quality, okay, quality, we can say how many. Okay, how many of an item are there is quality. Okay, how many of these items fit this category? That's qualitative. Okay, quantitative is how much of something do I have? How many pounds? How many ounces? How many kilograms? How many miles? How many of some unit? Okay. Okay, so we want quantity. That's what we're looking for in the ANOVA. This is for ANOVA is the quantity. The quality is when we do our chi-square goodness of fit test. Chi-square goodness of fit. That's for quality. Okay, ANOVA is for quantity. Okay, when we're comparing the averages of something, the average heights between different countries. Okay, the average population. Well, not maybe population. A good one. I don't know. Maybe the average smog levels between cities. Okay, something like that. The average distance that different cruise lines travel. Okay, are they about the same or are they different from each other? Okay, the calculations use StatCrunch. Okay, you could also use the calculator. I'll show you both ways. Okay, but typically you're just going to use some software to do the calculations. Okay, we typically let computers perform the calculations. You will not be required to perform any of the calculations on the final. Typical outputs are one-way ANOVA tables. Okay, you're looking for the F statistic and you're looking for the p-value. Okay. A small p-value, we reject the null. There is significant evidence of a difference in at least one of the means. A large p-value means we fail to reject the null. There is not enough evidence to show a difference between the means. So we accept that there's no difference here or no significant difference. There's going to be a difference, but it's not significant. Maybe I'll put that. No significant difference. If we fail to reject the null, then we would say mu1 is equal to mu2 is equal to mu3 is equal to mu4, okay, for all of the mu's, and no significant difference. Here, if we reject, that means there is a significance, it means at least one mean is different. Okay, at least one mean is different. Okay. See if I can enlarge that a little. It's good. A little bit better. Okay, next page. What statistics do we use? Well, we use what's called an F statistic. All you need to know for the F statistic is it's always positive. Okay, it's always right skewed. It's always skewed right. And it's always positive. Okay, and it follows 2 degrees of freedom. 2 degrees of freedom. Okay, I believe that's k minus 1 and n minus k. Okay, 2 degrees of freedom, k minus 1. We'll get to what the k's mean and the n minus k. So these are like rows and columns. Okay, 2 degrees of freedom. 2 degrees of freedom. Is that right? Let me make sure that that's right. Yep, k minus 1 and n minus k. That's good. I know my stuff. Okay. Below are dot plots of 6 samples taken from 6 populations. 3 were taken from normal populations with larger but equivalent variances. When you think variance, just think standard deviation. Okay, think standard deviation. Okay, they're basically synonymous. Okay, think standard deviation, ST. Okay, within each group, okay, 3 were taken from normal populations and 3 were taken from normal population, with larger variances, and 3 were taken from normal population with smaller variances. Okay. In both sample sets, it appears one of the sample means is larger. Okay, one of the sample means is larger, is higher than the others between their respective groups. Okay, so if you look at the large variance groups, this guy, the sample mean, this one is higher. This is the higher mean here than the other two respectively. And then over here, this third one is higher, has a higher average, right? Notice that the variances in the normal one group, the dots are way spread out in each of these. They're way spread out in each of these. Whereas in the small variances or the small standard deviations, they're really close together. Okay. It says, in which samples, the large or small variance, would you be more sure that one of the samples came from a population that has a higher mean compared to the others? So we're comparing to the others. Well, if I have a large variance, okay, a large variance, I can't be as certain that the mean is really that higher on average, that these means are really that much different. Okay, that this one and these two are really different because the data is so spread out that they can all be within a certain range where, yeah, I mean, the means could all roughly be about the same. Okay, but if the variances are much smaller, okay, then I know that the data is much more exact or precise. And so the means, okay, over their data set, the variation is so much smaller that this one is really different. It really could be different. Okay, different, probably. Okay, that is probably different than the other two. Whereas if you have a large variances, maybe not so different, okay, than the other two. Okay, so I would say that the in which set of samples, large or small, I'm going to say small, would you be more sure? So in the sample with small variances, in the samples, I guess I should say, with small variances, we would be more certain that one sample had a higher mean compared to the other two. Okay, so comparatively, we would say that, hey, if you've got small variations, okay, then it probably doesn't have the same average. Okay, they're probably not going to have the same average, you know. But if you have large variances, you've got dots all over the place, then it's going to be harder to pinpoint whether or not this guy is truly higher or not. Okay, is the higher mean guy here, is he really different? Is he really different? Well, maybe not. Okay, and that one is a probably. Okay. Okay, let's have some examples here of real numbers. Okay, so we have 7, 3, 6, 6. We have 6, 5, 5, 8, 4, 7, 6, 7. Okay, those are my 3 samples. And I want to know, is sample 1 comparatively the same as sample 2? And is that comparatively the same as sample 3? Are all of these 3 groups about the same? Well, they have the same sample size. They're all sample size of 4. They have means. One is 5.5, the other is 6.0, and the other is 6.0. That's pretty close. The sample means are pretty close. And the standard deviation squared, which is called the variance. So the variance is equal to S squared. Okay, so the sample variance is equal to the sample standard deviation squared. Okay, so S1 squared is 3.0, S2 squared is 2.0, and S3 squared is 2.0. So they roughly have similar variances as well. They're very similar data set. Okay. Okay. So we're gonna see, you know, we'll see what happens here. Hopefully we're gonna calculate these. Oh yeah, we do. We have to calculate it, which is good. Okay. Let's talk about if there's a lot more variance between samples compared to within, then the numerator will be larger, thus creating a larger F statistic. Okay, so they're just going back to this, the formula. Where's the formula? There it is. Going back to the formula. So they're saying if there's more variance between samples, this is very large, and this is very small. I'll make this be large. Okay, if the variance between samples is much larger than the variance within the samples, okay, then this has a large F value, then the F statistic is large. Okay, a large number divided by a small number is a large number. Okay, and that means that my p-value will be very small. So we would reject the null, that there's definitely a difference. And how does that play out with my data here? Okay, so what does it say? If the variance between samples, okay, the variance between the samples, or let's talk about the variance within the samples first. So the variance within the samples is small here. So this has a small variation within the samples. Okay, so within the samples is very small variation. That's what I've circled here, the small variation within the samples. Okay, and how is it compared to the variation between them? Well, I wouldn't say it's too big. I'd say that there's medium variation. Okay, medium variation over small variation. So between the samples, looking at, you know, how do they all compare to each other between the samples? Let's look at the means. How would the means compare between the samples? Well, the top two are fairly close to each other. The bottom, okay, is kind of not as close. So we have medium variation between, but small variation within the groups. Medium variation, that's still going to give me a fairly large, okay, fairly large. I mean, think of it as just like numbers. You know, think of like a medium number 1 to 100, right? What would be a medium number 1 to 100? Well, maybe about 50, right? 50, medium number 1 to 100. What would be a small number 1 to 100? Small number 1 to 100, maybe something less than 10, right? Maybe, I don't know, small number 1 to 100 maybe would be 10. Okay, medium number 50, small number 10. You would divide those two, you would get 5. Okay, and that's a pretty large F value. Okay, the F value is always going to be positive, but this is a pretty large F statistic. Okay, this is a large value. Okay, compared to the F statistic. Maybe this is 1. This is 2. This is 3 standard deviations. This is 4. This is 5. See how that's a pretty small p-value that we would be getting if we went up to 5. Okay, really small, which means that there's this one's probably definitely different than the other two. Now, how would this compare to the top one? Okay, calculating the F statistic. Again, it's between versus within. It's the variation between versus the variation within, right? Within. Okay, how does it vary within? How is the variation within? Well, there's a lot of variation within the groups. I'm going to start with the lower one first. There's large variation within the group. What about variation between the groups? Well, not a lot of variation between the groups. The means are fairly close together, so I would say that this is small variation really between the groups. Not a lot of differences in how the three groups behave. So let's do this in reverse. Well, this is small. What would be a small number? 1 to 100. Well, maybe, again, a small number would be like 10. Okay, and now I want a large number. What would be a large number from 1 to 100? Maybe a large number would be like 80, right? So when I divide that, what do I get? I get a really small number. I would get 1/8, which is 0.125. Okay, I get a really small number, and so if I look at my F value here of where 0.125 would be, maybe it would be something like here. Okay, we're not even to 1 standard deviation, and that would cover this whole thing. We would get an extremely small F statistic. F is small, leading to a very large p-value. P-value is large. Okay, because the p-value is the area. So it'd give me an extremely large p-value, and so I would not reject the null. I would say that these are behaving pretty much like each other. mu1 equals mu2 equals mu3. Okay, and again, don't confuse mu2 with a Pokemon. Okay, so mu3. Okay, mu1, mu2, mu3. Okay, I would say that HO, in this case, if that was my null hypothesis, I would not be rejecting that HO. Okay, do not reject this HO. Okay, because they're all about the same. Whereas down here, if this was my null, mu1 equals mu2 equals mu3, or maybe I could use 4, 5, and the 6 for these guys, just to differentiate them from the ones above. This is a 5 and mu6, right? So if that was, and then what's the alternative? The alternative always that there's at least one different, at least one that's different. So in this case, I would reject my HO. Okay, reject that HO. And I would accept the alternative, okay, that at least one is different. And which one's different? This guy here. One of these things is not like the other. One of these things just isn't the same. Okay, this one is a little different. Okay. Okay, so let's go back to our example. Okay. 7, 6, 4, 3, 5, 7, 6, 5. So what we really want to do with these numbers here is we want to get an F statistic and a p-value. That's what I'd like to do. And I'm going to use StatCrunch and the calculator to do this. Which one would you like to do first, StatCrunch or the calculator? I'll give you the choice here. StatCrunch or calculator to calculate the F stat and the p-value. P-value. Let's do StatCrunch. Okay. Can everybody see my StatCrunch? Jared, can you see my StatCrunch?
Not yet.
Not yet. Okay. Let me try to share it again. Okay. So how about now? You should be able to see it now.
Oh yeah.
Okay. So I'm going to type in what I need for this guy. Okay. So what was my so I'm going to type in my columns here, 7366. Okay, so let's go back here, 7366. Let's go to column 2. Okay, that's going to be 6558. 6558. Column 3 is going to be 4767. Okay, so 4767. Whoops, not 6. 67. Okay, now let's see what happens here. We're going to do an ANOVA on this thing. So an analysis of variance. So I'm going to go stat, and then I'm going to go to ANOVA, and I'm going to go to one way. So stat, ANOVA, one way. Okay, one way ANOVA. Okay, so stat, ANOVA, one way. Okay, selected columns is 1, 2, 3. That's correct. Okay, oh, do I need to select them? I think I could select them. So shift, select my three columns from my three different populations, my 3 different samples. And then I'm going to hit compute, and it gives me this nice little table that tells me how many is in it, tells me the mean, it tells me the standard deviation, and it tells me the standard error. Okay, but it gives me this nice ANOVA table. Okay, and let me see how I can do this. Let me see if I can go back and forth between the two. So I'm going to plug in the chart there. Okay, what I got from my table. Okay, from my ANOVA table here. Okay, the values that I got from my ANOVA table, I'm going to plug into the chart. So let me try to do this here. Let me stop sharing for a second. Let me share my desktop. Okay, hopefully that works. Okay, and so what are going to be my degrees of freedom? Okay, for the columns. Okay. Okay, the degrees of freedom for the columns was 2. Okay, and for the error was 9. Okay, so the columns, the degrees of freedom is 2, right? Because what is the columns? The column, the K is the number of samples or categories. Okay, so the number of samples that we have. In this case, K was equal to 3. So what's K minus 1? Well, that's 2 degrees of freedom. Okay, N is the sample size. How many were in the total sample? Okay, that's the sample size minus the number of categories. The total that's in the sample is the total values in all three columns. If I go back to the data here, okay, well, how many pieces of data do I have total?
Well, that's 12. I have 4 by times 3, which is 12 pieces of data. That's going to be n. That's the sample size. The sample size is 12 pieces of data, or four pieces of data in 3 samples. So that's 12 total pieces of data. So that's the n. The n is the 12 for the sample size. So the error within, okay, the denominator degrees of freedom is going to be n minus k. N in this case is 12, okay, minus 3, which is the number of columns that I have. Okay, k is the number of columns, which is going to be equal to 9. So this is 9, and the total is 11. The total degrees of freedom is 11 that way. We add them up, and we get our total degrees of freedom. Okay. The other values aren't as meaningful for us at this point. The SS stands for sum of the squares. Okay, what are the sum of the squares? Okay, we'll just plug it in here. Okay, what is it? It's 0.6 repeated and then 21. Okay, so 0.6 repeated, so 0.6 repeated, and then 21, which is going to give me 21.6 repeated. Okay, what's the mean squares, or the average of the sum of the squares? This is going to be 0.3. And how did they get that? Well, they just divided 0.6 by 2, okay, by the degrees of freedom. Okay, and then 20, and then we're going to get 2.3 for the mean sum of the squares for the error. And the way we get that is we divide the sum of the squares column by the degrees of freedom. 21 over 9 is 2.3 repeated. So that's the mean sum of the squares. Okay, and that will give me an F statistic, which is 0.14285. So a pretty small, or I should say 286. I'll just put 29. Okay, a pretty small F statistic, which is going to lead me to a pretty large p-value. This is a pretty large p-value. Is this p-value less than 0.05? Is it less than 1.05? No. Okay, it's not, which means that I do what? I accept the null in this case. If this HO, I would accept what? That the means of all 3, this should be a 2, and this should be a 3. The means of all 3 of them are roughly the same. Okay, that the groups behave roughly the same. Okay, which that makes sense. mu1 equals mu2 equals mu3. Okay, so do they behave roughly the same? Well, are these values roughly close to each other? Yeah, very close to each other. Okay, are they roughly, around the same values? Is the mean around the same values? Yes, absolutely. Is the standard deviations or the variances very similar? Yeah, the variances are very similar. Okay, the standard deviations are very similar. So we would not. Okay, what would the numbers look like maybe if we did reject? If they were different, what would maybe, I don't know, maybe let's use maybe 4. We'll still have a 4. Maybe we'll have like a 17. Okay, maybe a 61 here. Okay, and I don't know. We'll leave that as 7. Okay, what if I just change those 2 numbers there? The means would be very different, and the variance would be the standard deviation would be extremely different here, right? Okay, so let's run this one more time with this data, just changing those 2 to 17 and 61. Let's see what happens to my F statistic. I would think my F statistic would get higher and my p-value would get lower. Let's go to stat, one way ANOVA. Let's select our 3 columns and let's hit compute. And what happens to, well, my F statistic went up. Okay, it did go up, and the p-value, it's still, they're still saying don't reject, that these are close enough to not reject. Let's see what would happen if I, what would these numbers have to be to really reject? Because we've got kind of a pretty far variance. What if I did this? What if I said, hey, we're going to take this and we're going to do 16, 17, 18, and maybe 20. Now the variation is really close together. The variation is really close, but they're much different. They're much farther away for the third one. Let's see what happens there. I think the F statistic is going to go even higher in this case because the variance is getting slower, which means the number we're dividing by is much smaller, or the number that we have on top is much smaller. Okay, so let's go to stats and ANOVA and one-way ANOVA, and let's compute this. Okay, compute this, and what are we getting? We're getting an F-stat now of 72. Wow, that is huge. And a p-value of basically 0. And what does that mean? It means that they are not the same, that they are not similar, okay, that they are extremely different because, yeah, this group over here that, you know, the average of group 3 is certainly much different than the average of groups 1 and 2. Okay. Okay, so that one is extremely different. Okay, much more different than just changing 2 of the numbers. When I change all 4 of them and make them numbers that are very close to each other, then I get a large F statistic, excuse me, and a small p-value. Okay, now let's do this on the calculator. How would I do this on the calculator? Okay, let's go to the calculator now. Okay, so let's go to turn it on. Okay, and then I want to go to edit, stat, and then edit. And I want to plug in my values into list 1, list 2, and list 3. Because I want to compare the 3, right? So list 1 is 7, 3, 6, 3, 6, 6. Okay, what's list 2? List 2 is 6, 5, 5, 8. 3 is 4, 7, 6, 7. Okay, I'm going to quit out of that. I'm going to go second, or not, I don't even do second, just hit stats. Just hit stats. And we're going to go to tests. And I'm going to actually arrow up this time because ANOVA is the very last one. So instead of going all the way down to ANOVA, I'm going to go and I'm going to go up. I clicked up to get there. I'm going to click up, and that's going to be ANOVA. And then it's going to say ANOVA on what? What do we want to do ANOVA on? And I just have to list the lists that I want to compare. So I want to do a second L1. I want to compare L1, comma, to second 2, L2, comma, to second 3, and I want to compare those. Okay, and I'm going to run those numbers, and this tells me that my F statistic should be 0.148, 1429. Sorry, 1429. My p-value was 0.8.
0.688. Okay, and that's exactly what we found on StatCrunch. Okay, what are the degrees of freedom? Oh, sorry. Okay, what were the degrees of freedom? Okay, the degrees of freedom for the factor, okay, that's between the groups, that's going to be 2. Okay, and then then the sum of the squares for the columns is 0.6 repeated, and the mean sum of the squares, or the average, is 0.3 repeated. Okay, the error is the between, okay, is within, sorry, within. Okay, the error within. Okay, degrees of freedom is 9. So, sum of the squares was 21, and the mean of that, the average of that would be, okay, 2.3. Okay, and then they give you some sample standard deviations there for the whole thing. Okay, but that's one way ANOVA. Okay, so that's how you do it on the calculator. Okay, I think it's much easier doing it on the StatCrunch personally, so I'm going to do example 2 using StatCrunch and not the calculator. Okay, since I have both of them available to me. It's just more time consuming on the calculator because you have to plug in those lists instead of typing them with a keyboard. And okay, so let's go through example 2 here. Okay, a car company, okay, is testing their miles per gallon of one of their car models along with 2 similar models from 2 other companies. A random of 5 cars are taken. Okay, random 5 cars were taken from each company, and their MPGs were MPGs after 100 miles were recorded. Okay. Miles per gallon, right? So take 100, divide by the number of gallons used, and this is the miles per gallon. Is there sufficient evidence to show a difference in at least one of the car's models? Okay, is one of the car's models significantly different? Use a 0.10 significance level. Okay, so what do we want to do? We want to do 5-step method. Okay, so we want to say, what's our null going to be? What's our null hypothesis and our alternative? Our null is that mu1 is equal to mu2 is equal to mu3. Okay. If it was 2, only 2, I would do a not equals here. Mu1 is not equal to mu2. If we're only doing a 2 sample t-test, then I would do not equal. Mu1's not equal to mu2. But in this case, we are comparing 3 of them. We say that at least, our alternative is at least 1 is different. Okay, and this makes it so that I don't have to write the following. Mu1 is equal to mu2, but not equal to mu3. Mu1 is not equal to mu2, but mu2 is equal to mu3. Mu1 is what are the other ones that I could have? Mu1 is not equal to mu2 and not equal to mu3. Okay. What else could I have? Anything else that I could have? Mu2 is not equal to mu1, but it is equal to mu3. Mu2 is not equal to either of them. Mu1 is not equal. So instead of writing all that, okay, I just replace that with this statement. Okay, that just means at least 1 is different. Okay, so we don't write this. We write at least 1 is different. Okay, so I'm gonna actually get rid of that so I can save space. Okay, number 2. Number 2 is, what test are we using? What test are we using? We're using a one-way ANOVA. Okay, one-way ANOVA F test. The F test. Okay, number 3, are these independent? Are they random? You know, we're going to assume all conditions are met. Assume all conditions are met. Okay, number 4, this is where we actually calculate the statistics. F equals and the p-value equals. Okay, p-value equals. And then number 5, we're going to have our conclusion based on these. Okay, so let's use our values here and plug that into StatCrunch real quick. Hopefully it didn't log me out. Nope, it didn't. That's good. Okay, so let's plug in our statistics here. Okay, so for our first one here, we're going to have 27. Goodbye. Okay, 27, 26. Yes. Okay. 26, 29, 31, 30. Okay, 28, 29, 26, 31, 27, 32, 29, 28, 33, 34. Okay, if you had to make a guess, would you say that these are pretty similar to each other? They're all pretty similar to each other, or that there's one or more that are different? What would you guess would be the outcome here? Are they all pretty close to each other? You know, is there a lot of variation within the groups? Is there a lot of variation between the groups? Okay, or are they all pretty much the same? Okay, well, I mean, the range of values isn't too much. They all seem to be, you know, right around the upper 20s, lower 30s. Okay, and they don't seem to vary too much. So I would say that the F statistic is going to be pretty low in this case. And the p-value is going to be pretty high, which means that I will probably not reject my HO. Okay. And they're probably going to be all very similar. I mean, just looking at the data. But let's not take just a visual, you know, kind of, you know, just going with what this visually looks like, you know, oh, it's about the same. Let's actually run a hard statistic. Let's do our ANOVA. Okay, and we're going to hit shift, hold shift down, and then I can get all 3 of those. Okay, and then I want to compute. Okay, and I'm going to pull this guy over here. Okay, so what was my F statistic? My F statistic was, well, it was actually kind of high. Not a lot of variation between or within. So, you know, this one seems to be maybe a little higher than the other ones. Well, I don't know. It all depends. Okay, but still, okay, still what's the outcome regardless, you know, what's the outcome here? The F statistic is 2.707, what's the p-value? It's 0.107. So is this less than 0.10? No, it's not less than 0.10. And so what's our outcome? Our outcome is that we do not reject the null. And so we could say, okay, since the p-value, okay, is greater than 0.10, which is our significance level, we fail to reject our HO. Okay, we fail to reject our null. Okay, there is insufficient evidence to suggest any difference, and put it in context of the problem. What was the problem? Well, it was miles per gallon, right? Any differences in MPG between the three models. Okay. Between the three models. And that's it. That's why is that floating like that? Weird. Okay, so if you want, I'll do this on the calculator. You can sit around and I'll do this on the calculator as well. Just for kicks and giggles, but I'm done with the notes at this point. Okay. Okay, due on Thursday is homework from this section and your take-home exam for chapter 12. It's worth 50 points. It's worth half an exam score. So if you answer all those questions correctly, okay, this could really boost your exam grade. Okay, so just keep that in mind. And it is due by 6 o'clock. Okay, you will get marked off points if you turn it in after 6. And if your homework and your take-home exam are done, you do not need to log into class on Thursday. Okay. Okay, so let's hopefully that's incentive for you to get this done. Okay, if it's not done, I'm going to be hunting you down and emailing you and saying, hey, you need to come to class and finish your work. Okay, I don't want to have to parent you at this stage in your life, but I will do it. Okay, if I'm forced to. Okay, I will mirror the maturity level that I am given. Okay, well, I won't mirror it because that would mean that I would be succumbing to a lower level of maturity. But I will impose the necessary restrictions on immature behavior. Okay, or I shouldn't say immature, I should say irresponsible. Yeah, it's more of an irresponsible. I guess those two go hand in hand. Okay, just get it done. You know, that's all I have to say. Okay. Okay, let's go to stat. Let's go to edit. Let's edit these lists. Okay, and see if the calculator doesn't give us the exact same thing that we got on StatCrunch. 26, 29, 31. Okay, and 30. Boom. Plug that in there, enter, and move it over to the next list. 28, 29, 26, 31, 27. Okay, arrow that over, arrow up, 32, 29, 28, 33, and 34. oops, not 3, 33. Boom. Okay, so now again, we're going to go to stat, tests. I'm going to arrow up and hit enter. And I have to tell it which list that I want to use. Oops. And close my parentheses, and it gives me the exact same F statistic and the same p-value. And I am good. Okay, so I'm going to stop my sharing at this point. Okay, if you have any questions, that again, that is everything. We've covered everything, every topic in the class at this point. That's why there is no lecture on Thursday. Again, usually I put in a class where I have to be absent, or my kids, something happens with my family, but that didn't happen this semester. So we have one extra class period and that you do not need to show up to. So no class on Thursday if you turn in your assignments on time. Okay. Okay, if you want to stick around and get some tutoring on your homework, let me know. Me and me will be around to help you here. Okay.
Professor,
Yes.
on today's homework, the last problem is talking about pooled data with t-tests.
Oh, okay. Pool data. Okay, yeah.
I was just wondering if you could speak on that a little bit,
Sure.
just because I didn't really learn about it.
Yeah. So a t-test with pooled data. I think you just change the setting in your calculator for that to, instead of, and it you just says pooled and then you put on yes. But let me check real quick. So let's see what we got here. Log into Canvas. Logging in. Math 219. Arrow down to today's stuff. Okay, so one-way ANOVA, that's what you're looking at? Okay. So one-way ANOVA F test. I think there's only 3 questions on this one, I believe.
Correct.
Okay. So we want the last question here, I guess. That's question number 2. So question number 3, you plug in treatment 1, treatment 2, right?
Mm-hmm.
Okay, so the following represent the results from an independent measure study. Okay, this is more like using technology run a one-way ANOVA test. Okay. Now run the 2 independent sample test. Do this with pooled variances. Okay, and they would just want you to compare because there's only two samples here. You could have done a sample t-test, 2 sample t-tests basically. Okay, and they're saying pool the variances, which means roughly, which means that the two are not independent; they're dependent on each other. Okay, so it's saying just to compare, as a comparison, they're going to do. We're going to plug these into our list, right? So let me go to stat and then edit. and plug these into the lists. I'm going to clear list 3. Okay, and I'm going to edit list 1 and 2. So this is 6.3, 7.1, 5.6, 7.2, 7.5, 7.6, 6.2, and 6. That's correct. Okay, and then we go 4.9. Okay, 6.6, 5. Okay, 5.2, 5.2, 5, 5.6, and 5. Oops, I screwed up somewhere. Where did I screw up? Oh, it's because I didn't clear the list. Okay, 4.96, 0.65, 5.2, 5.2, 5, 5.6, and then 5. Okay, there we go. That looks good. Okay, so we're going to do stat. And the initial thing that we would get is we would do our test and we would do an ANOVA on this, right? So we do an ANOVA on list 1 and list 2. Okay, and we would say, oh, well, we're going to get an F statistic of 17 and a p-value of 0.001. That's a really small p-value, which means that those two are definitely different. Okay, there's a definite difference between the two lists. Okay, one has much larger variance than the other one, and the means are not the same. Okay. Okay, so, but they're saying we could have also run the test if we did a pooled variances, because we're comparing the variances, we're comparing the variations. So we want to pool them. We want to cross them over and compare the variances one to another using a 2-sample t-test. So let's go to stats, calc, or sorry, not calc, test. And we want to do a 2-sample t-test. That's number 4 here. Okay, and we're going to use data for this. Data, and it says, hey, are you going to list 1? Yes. List 2? Yes. Do we know if they're difference? No, I don't know. I just wanted them to be different. Are they different from each other, right? Not equals. We don't care about greater than or less than. We just care if it's not equal to. And then it says, are the variances being pooled? And we would click on yes, the variances are being pooled. And then we would calculate and we would get, look at that. It's almost the exact same p-value that we got before. Okay, and so they're saying, look, you would get the same p-value doing it either way. Okay, now I don't teach that way of doing it simply because I think it's too confusing. It's if you know how to do the ANOVA, you know how to get the right p-value every single time. So they're just saying that you could have also done it this other way, blah blah blah, that I didn't really cover in the course. Okay.
I was just wondering then, why would you ever do the 2-sample t-test with pooled variances if you could just do a one-way ANOVA and get the same result?
Yeah, I that's for a much higher level course than this one. That's one of the reasons I don't teach it. So
Okay, thank you, Professor.
it's a way above the, I think it goes to, the nature of what you're trying to compare.
Okay.
Yeah.
Thank
For all intents and purposes, they are the same. It's just I don't want to confuse people, but yeah, it's confusing when they ask for those values on the homework and you don't have any frame of reference. Okay.
Sounds good. Sharing my screen at this point.